Hello everyone, we are looking at an example using Norton's theorem, and in Norton's theorem we're going to apply a few tactics here and there. So the first step, the question reads, use Norton's theorem to determine the current flowing the 10 ohm resistance for the circuit below. So what happens is, whenever you ask to do that, you short circuit the branch. You short circuit the branch where you want to determine the current. So the first step will be the solution. Remember, because this resistor is in series to this one, so we're going to short circuit the whole of this branch. So we shall have, so the first step is short circuit. Short circuit the branch containing the 10 ohm resistor. So the circuit remaining will be, we have 10 ohms there, we have a resistor of 2 there, this is our R2, which is 8, and we have short circuited the whole of this branch. This is what we are calling the short circuit current. So the whole of this branch has been removed. And once that happens, remember, when you short circuit, it means you bypass. So basically you are bypassing this resistor. So current will avoid this branch. So current will just take this circuit. So, and if you want to get the short circuit current, the short circuit current will be equals to the total voltage, which is 10, divided by the total resistance, which is 2. Remember, this one is as good as it has been removed, because whenever current flows, it will decide to pass through this easier branch, the short circuit branch, than using this route. So you divide by the 2 ohm resistor. So this gives us 5 amperes as the current that is flowing in the circuit, as the short circuit current. After that, you now need to get the total resistance. And the total resistance, of course, is obtained by removing the EMF. You need to remove the EMF. So, total resistance by removing EMFs. So if you remove the EMFs, the circuit will appear like this. You will be having 2 ohms there. You will be having 8 ohm here, like that. Then remember, this is the resistance we are talking about. The resistance will be obtained looking in from the branch. And you can see we are only having 2 resistances remaining. So the total resistance there, R, will be equal to product sum, 2 times 8 all over 2 plus 8, which becomes 16 all over 10, which gives us 1.6 ohms. That is the total resistance. After you do that, you need now to draw the Norton's circuit, which will be drawn as a parallel. It is presented as a parallel circuit, where we shall have, we have the voltage there as 10. We have the internal resistance. This R is presented as 1.6 ohms. Then you also now need to bring back the branch that you removed. Remember, you removed this branch, so you need to return it back. So the branch has got 2 resistors, which is 5 ohm, and it also has 10 ohms. Remember, our interest is to get the current flowing across the 10 ohm resistor. So if you get the current flowing in this branch, you will be able to determine the current that is passing through the 10 ohm resistor. So basically, we can use current divider rule, which says if you want to get the current that is passing through this. So basically, remember we have said the current flowing here, the short circuit current flowing is 5 amperes. That is the current which is flowing in the circuit. So after that, we now need to get the current that is passing through this point. We use current divider rule, which basically states that if you want to get current in this branch, you use the resistor, the opposite resistor, or the neighbor's resistor. So current passing through the 10 ohm resistor will be given by 1.6. We are using this resistor over the total resistance, this plus this, 1.6 plus 5 plus 10. Then you multiply by the total current in the circuit, which is 5. Of course, this is 1.6 divided by, this is 6.6 plus 10, 16.6 times 5. So this should give us, if you use your calculator, it will be 1.6 divided by 16.6 times 5. It gives us 0.482 amperes. So that is the current that is passing through the 10 ohm resistor using Norton's theorem. So we're going to stop there.